So in the last lecture, what we did, during lab, was we found what the empirical formula was from a percent composition. So today, we're going to continue working on that using combustion analysis. But before that, I wanted to show you a special case that doesn't quite turn out as pretty whole numbers as the example that we did in lab did. So this was the example that we did in lab. So this is the way these questions usually look. Determine the empirical formula of a compound given the following percent compositions. So our steps were assume a sample size. Now if we're dealing with percentages, what's a good sample size to assume to make our math easy? 100 what? Grams. 100 grams. So if I assume 100 grams, I can take these percentages and turn them into grams. Then what do I do now that I have grams of both elements? Take those grams and convert them to what? Moles. So how do you go from grams to moles?
Divide molar mass?
Perfect. Divide by molar mass. So we take the elements that we've converted to grams. So in this case, we'd have 30.45 grams of nitrogen and 69.55 grams of oxygen. Divide by the molar mass of each. Molar mass of nitrogen, 14.01. Molar mass of oxygen, 16. That gives us moles. So, in this case, we have moles. Now, what do we do at this point here where we had moles of each, but they weren't nice, pretty whole numbers here? This point where we had moles of each. Good. We picked the smallest number, which is the same thing we did in lab. We picked the smallest number, which in this case is the 2.17, divide both of them by that number. And in this case, that gave us a ratio of 1 nitrogen to 2 oxygen. So it was a nice, pretty whole number. Now, the problem is, does every empirical formula have one element that there's only one of? No. So how do you end up with an empirical formula that one of them didn't simplify down to 1? So this is the example problem I was going to start off with today. This is checkpoint 3.4.4 on page 99 of your textbook. And I'm going to go ahead and tell you this one is not going to end up being a pretty nice whole number ratio, or pretty nice whole number ratio, so it means you're not going to end up with one of them simplifying down to just 1. So let's go ahead and work through this problem. Determine the empirical formula of a compound that's 48.6% carbon, 8.2% hydrogen, and 43.2% oxygen. So what's the first step? Good. Convert percentages to grams, assuming a sample size. So we're going to assume 100 grams again to make our math easy. We have 48.6 grams of carbon, 8.2 grams of hydrogen, and 43.2 grams of oxygen. What's our second step?
Convert grams to moles.
Good. Convert grams to moles. And you go from grams to moles by dividing by molar mass. So when we do that, grams will cancel and we'll be left with moles of each. And I'm not worrying about significant figures because we're trying to get at the end to kind of a whole number here. So once we have moles of each, those aren't whole numbers, so how do we get to a whole number ratio? Good. So in this case, what's our smallest number? Good. The 2.7 is the smallest, so we're going to divide each of these by that 2.7. So that'll give us 1 of the oxygens. 3 of the hydrogens. And the problem up here is when I take 4.05 divided by 2.7, what does that give me? 1.5, which does not round to 2. It's not close enough to round to 2. It does round close to a fraction. What fraction is it? 3/2. So I'm going to write this as 3/2. Now, in this case, the hydrogen, I got 3.01. That's close enough to 3. I can just call that 3. But if it's not that close to a whole number, it's really closer to fraction, and you have to write it as the fraction is closer to. So if it was 0.334, you would write it as a third. 1.5, you would write as 3/2. So here's what our empirical formula looks like at this point. Carbon, 3/2, hydrogen, 3, and then just 1 oxygen. Now, in the last lecture, when we were balancing equations and we balanced out the equation for the combustion of butane, we ended up with a fraction temporarily in order to balance it. What did we do to get rid of that fraction? Good. We multiplied the whole thing through by the denominator. So we can do the exact same thing. We can multiply through the whole thing by the denominator here. So we're going to multiply this entire equation by what? 2. So when we multiply through by 2, that gets rid of that 2. That turns this 3 into a what? And that turns the oxygen into a 2. So now my new empirical formula is C3H6O2. Is that still an empirical formula? It looks like it. How do I know that it's an empirical formula? Is there any common factor here? No, 3, 6, and 2 do not have a common factor. Well, except for 1, yeah. So we know it's an empirical formula because there is no common factor. This is a question I see missed a lot on the first test. When it asks you to find an empirical formula given the molecular formula, you have to simplify it all the way down to where there are no longer any common factors. So this would be my empirical formula, which, if you're looking at the book, is answer E. So again, if you get really close to a whole number like that 3.01, you can assume it's the whole number. But if you're really much closer to a fraction, then write it as the fraction. Multiply your entire empirical formula through by the denominator to get rid of that fraction. How do we feel about that? We're good? Ready to add a little bit more complication to it? All right. So in that case, we were given the percentages of each to find the empirical formula. In the next section, we're going to use an analytical technique called combustion analysis to determine what that empirical formula is, and then use that to determine the molecular formula. So knowing the mass of each element contained in a sample size can give us the empirical formula. That's what we just saw. We can get those mass percentages, go to the empirical formula. But one way to get there is through combustion analysis. What is combustion again? We're burning it, right? So the idea behind combustion analysis is I have some sort of compound. I don't know what it is. And I'm going to burn it to determine what it is. So here's what goes on. I've got some sort of sample here. So here's my sample. I don't know what it is, but I know that the sample contains carbon, hydrogen, and possibly oxygen. I just don't know what this ratio is. Some carbon, some hydrogen, may or may not have oxygen. So some sort of an organic compound here. When I burn it, the two products of combustion are what and what? Water and carbon dioxide. So I'm going to absorb the water, the carbon, or the copper oxide there is just absorbing impurities, absorb the water and absorb the carbon dioxide. Now, if I know what mass of my sample I start with, and I completely burn it so there's no more of it left, every gram of carbon that was in my starting sample ends up in what product? CO2. So every gram of carbon that I started ends up in the CO2. Every gram of hydrogen ends up where? In the H2O. Now, oxygen is tricky because we need the fuel to burn, but what other reactant is in combustion? Oxygen. So when we look at the oxygen and water and the oxygen carbon dioxide, some of it might have come from the sample, but a large portion of it probably came from the oxygen that we're piping in to keep the fire burning. So we can't use the same technique to determine oxygen. However, if we know what our starting mass is of the sample, and we determine how many grams of carbon and how many grams of hydrogen, if there's any mass unaccounted for, that must be oxygen. If grams of hot carbon plus grams of hydrogen adds up to the grams of the sample, then we just know there was no oxygen in that sample. Like the butane that we saw last time had no oxygen. Yes?
You're going to need to remember this?
No, you're just going to need to know how to go through the process and determine the empirical formula. But no, I'm not going to ask you to diagram this on the test. Yeah. All right, so let's look at a reaction. So in this particular equation, we are told what the starting compound is. On the test, I'm not going to tell you what the starting compound is, because then you could just find out what the formula is if you know what the formula of glucose is. So in the same thing on the homework. I think on the homework it tells you what the compound is, but if you just look up what is the formula for, I want to say it was vitamin C is your homework question or something like that. If you just look up what the formula is for vitamin C, that's not going to help you very much come the test day when you won't have Google to help you. So make sure you know how to do this process. There will be one of these on the test on Friday. So looking at this sample problem, it says, suppose that in one such experiment, the combustion of 18.8 grams of glucose produced 27.6 grams of carbon dioxide and 11.3 grams of water. And we can calculate the mass of carbon and hydrogen in the sample using the mass of carbon dioxide and water. So again, let's write just a simple equation to kind of keep track of what we're doing here. Glucose. Pretend we don't know what the formula is glucose is, but we know it contains carbon, hydrogen, and oxygen. We just don't know what ratio. Combustion. What's this going to react with? Oxygen. Good. What are the two products? Good. CO2 and H2O. I'm not really worrying about states of matter right now. So what we're saying is that every gram of carbon from our original sample ended up in the carbon dioxide. So these grams will be equal. So first of all, let's determine grams of carbon in our carbon dioxide. We're told that we have 27.6 grams of carbon dioxide. We need to take those 27.6 grams and break it down to just grams of carbon. So here's our steps. Take those grams, convert them to moles. We do that by dividing by the molar mass. Molar mass of carbon dioxide is 44.01. How did we find 44.01? Good. Adding together the atomic masses of carbon, 12.01, 2 oxygens at 16 apiece, adds up to that 44.01. Now, at the end of this step, we will have moles of carbon dioxide. We can then use the molar ratio, how many carbons is in a carbon dioxide, which is 1, so this ratio is 1 to 1, to get to moles of carbon. Once I'm at moles of carbon, I can get to grams of carbon using the molar mass of carbon, but now moles to gram, you multiply by the molar mass. So we're going to multiply by the molar mass of carbon. So of that 27.6 grams of carbon dioxide, we work out that 7.53 grams of it must be carbon. We do the exact same process for water. To find the mass of hydrogen, we take our 11.3 grams of H2O, divide by the molar mass of H2O, which is 18.02, multiply by the molar ratio. So molar ratio says that there are 2 hydrogens in every water because it's H2O, right? So that's where it's 2 to 1. Then we'll end up with moles of hydrogen at the end of this step. So to get to grams, we multiply by the molar mass of hydrogen, which is 1.008, and we're left with grams of hydrogen. So of those 11.3 grams of water, we're left with 1.26 grams that were hydrogen. So of our 18.8 grams of glucose, 7.53 grams were carbon and 1.626 grams were hydrogen. If we subtract off those two, good, we'll get the difference, which is the amount of oxygen. So minus 7.53 minus 1.26. .01 grams is the leftover mass. So this must be grams of oxygen. Now, if I ended up with pretty close to 0 grams, I would just assume that my sample didn't have any oxygen in it. At this point, I am at step 2 of the last problem. I have grams of all of my elements. The last problem, we went from percentage straight into grams really easily. This one just took more steps, but it's the same idea. we need to get grams of each of this element. By the way, this sample problem is on page 100 if you're following along in the textbook. So now at this point, I have grams of each element. What was my next step from the last problem once we were grams of each element? That was once we had moles. They were still in grams. Empirical formulas are molar ratios, which means you must be in units of moles. That's a common mistake, is to divide by the smallest number right here, but you're in grams. Empirical formula is not the gram mass ratio, it's the molar ratio. So what must we do to all these grams? Convert them to moles. Good. How do you convert from grams to moles? Good. Divide by molar mass. So we're going to take this 7.53 grams of carbon divided by the molar mass of carbon, 1.26 grams of hydrogen divided by the molar mass of hydrogen, 10.01 grams of oxygen divided by the molar mass of oxygen. There. And now we have moles of carbon, moles of hydrogen, moles of oxygen, and there's our ratio. Now, what's still looking wrong about this ratio here? It's numbers. It's what kind of numbers? Decimals. We don't want decimals. So how did we get rid of the decimals last time? Divide by the smallest number. So what's the smallest number in this case? 0.6. Good. 0.626 moles of oxygen was our smallest number. 626. 0.626, 0.626. Now, 0.627 divided by 0.626 is pretty darn close to what? 1. So we're going to say it's about 1 carbon. And 1.25 divided by 0.626 is pretty darn close to what? 2. And then, of course, divided by itself is 1. So our empirical formula is not this. It's what? Carbon, hydrogen, oxygen. What are our subscripts here? 1, 2, and then understood 1. So that is our empirical formula.
So where does the oxygen that fuels combustion?
If you actually look at our starting masses here, 27.6 grams and 11.3 grams. When you add those together, it's much greater than 18.8 grams. So that extra mass is accounted for by the extra oxygen that came in the reaction. So here's our empirical formula. So the last step, if you are given the molar mass, you can go from the empirical formula to the molecular formula, but you have to be told what the molar mass is. Now in this case, we are told what the molar mass is. We are told that the molar mass of glucose is approximately 180 grams. So our empirical formula is CH2O. I want to know what is the molecular formula given the molar mass is 180 grams. Now, as we learned in Chapter 2, sometimes the empirical formula is the molecular formula, the same thing, in which case the formula of our empirical formula, or the molar mass of our empirical formula, should be equal to the molar mass of the whole thing. Let's see. And we're dealing with pretty close to whole numbers here, so we're just going to use the whole number masses here just to kind of estimate, make our math easy. If we want to estimate what the mass is of a carbon, we're just going to say 12. Of 2 hydrogens, just 2. And of an oxygen, 16. So what does that add up to? 30. So the mass of one formula here is about 30 grams per mole, which is not 180. But it is divisible into 180. 180 divided by 30 is a ratio of what? 6. Which means that to get to our empirical formula, our molecular formula had to have been divided by what? 6. So if we want to go backwards, we should do what? Multiply by 6. Good. So we're going to take our empirical formula, change colors here, and we're going to multiply through by 6. So now that gives us, good, C6H12O6, which, if you know, is actually the molecular formula for glucose. So if you are given the molecular mass or the molar mass, you can determine the molecular formula from the empirical formula by figuring out what this ratio is of the masses. All right. Ready to try an example of this? Go through all the steps at once? Yes. Okay. The combustion of a 5.50 gram sample of benzene, again, we're pretending we don't know what the formula of benzene is, and on the test I won't even tell you what the name of the compound is, produces 18.59 grams of carbon dioxide and 3.81 grams of water. Determine the empirical formula and the molecular formula given that its molar mass is approximately 78 grams per mole. Yeah. No, I don't. On the test, I don't require you to show your work, but if you want any partial credit on a calculation, I can't give you partial credit if I don't see any work. So I don't require it, but if you want to get partial credit, it's helpful. Yeah. Get some blank slides here, some working space here. All right. So I like to start by writing out a reaction formula so I can keep track of all of these numbers. So benzene, again, we're going to pretend we don't know what the formula is. We just know it contains carbon, hydrogen, possibly oxygen. So pen. Carbon, hydrogen, possibly oxygen, question mark, question mark, question mark. Reacts with O2 to form CO2 and H2O. Now, we have 5.5 grams of that benzene. We produced 18.59 grams of carbon dioxide. And 3.81 grams of water. 81. Yes.
Could you explain to me, like, okay, because mathematically it just doesn't make, like, I mean, I understand that benzene is, as a whole is a compound, so like the entire molecular mass is like, okay, but if it's like 5.5 grams of that, like, if it's all in grams, like, why doesn't the products, like, add up to 5.5?
Because there's another reactant here, oxygen.
Okay.
You don't know how many grams of oxygen are
All
there.
right, thank you.
Yep. But that is a good question. Yes, mass must be conserved. We know that. Mass must be conserved. And that's because there's some unknown amount of oxygen in this reaction.
Cool, yeah.
Yeah. All right, so first of all, let's find grams of carbon. Find grams of carbon. What are we going to use to find the grams of carbon? Carbon dioxide, good. So I have 18.59 grams of CO2. What's my first step? Take grams and do what with them? Good. Divide by the molar mass of CO2 to convert to moles. When in doubt, usually the first step is to convert to moles. If you see grams and you don't know what to do, at least convert to moles and you'll probably be halfway there. So convert to moles by dividing by molar mass. CO2 has a molar mass of 44.01 grams per mole. The good news is these molar masses are going to be the same because carbon dioxide is involved in every combustion analysis problem you will always do. And that number is always the same. Actually, let me just write this down so we have space to keep going the way they did it. So times 1 over, why does it love doing those horizontal lines? 1 grams per mole. And that will leave us with moles of CO2. What was the next step? Once we're at moles of CO2, we just want moles of what? Carbon. So the next step is what we call molar ratio, which is the ratio of carbon to carbon dioxide. What is that ratio? Good. 1 carbon to 1 CO2. So now we're still at moles, but now we're moles of carbon. But we want what of carbon? Grams. So last step, how do you get from moles to grams? Good. Multiplied by the molar mass of carbon, which is 12.01 grams per mole. Make sure all of our units keep track. Okay, so right here, first step, grams cancel with grams. Next step, carbon dioxide cancel with carbon dioxide. Last step, moles cancels with moles, and we're left with just carbon and grams, which is exactly what we want. And now multiply across and divide by everything that was in the denominator. Getting 5.07 grams of carbon. Everybody get that? Next step, we have grams of carbon. What are we going to find grams of next? Hydrogen. Good. So we're going to take that 3.81 grams of H2O, and we're going to do the exact same thing. Convert to moles by multiplying by 1 over the molar mass. Molar mass of water is 18.02. Now the molar ratio. Once I'm at moles of water, I want moles of just what? Hydrogen. What's that ratio going to be? 2 to 1. Good. There are 2 hydrogens in every 1 water. Good. And then lastly, take those moles of hydrogen, get back to grams by multiplying by the molar mass. Molar mass of hydrogen is 1.008 grams per mole. Grams cancel with grams, water cancels with water, moles cancel with moles, and we're left with hydrogen and grams. .426 grams of hydrogen. Hydrogen doesn't like to be getting that close to the edge, apparently. Now, how do we find out if there's oxygen there? Good. Add those together and subtract it from our total mass of benzene. So 5.07 plus 0.426 adds up to what? 5.496, which we've only got 2 decimal places, so that rounds to what? 5.50 grams. So, did we have any grams of oxygen?
No.
Nope, because that's 5.5 grams, and we ended with 5.5 grams. So that means that there must not be any oxygen in benzene.
So the 5.50.
Mm-hmm.
Oh, so you're saying that we added the 5.07.
Yep. We added 5.07 plus 0.426, and then I rounded to 2 decimal places, since there were only 2 decimal places in this number. So now I have grams of carbon, grams of hydrogen. I'm at the same place I was at step 2 of the practice problem we started today with. So what do I do with those grams? Convert them to moles. When in doubt, convert to moles. So we do that by dividing by molar mass. And that will give us moles of carbon and moles of hydrogen. Boy, those horizontal lines are getting more frequent. So once we have moles of the two of them, what's the next step to get that to a whole number ratio? Good. Divide by the smallest number, which in this case, smallest number is 0.422. Or just looking at those two numbers, what can we assume is the ratio? 1 to 1. So what's our empirical formula? CH is our empirical formula. Stop doing those horizontal lines. I have no idea. It is really annoying, though. But this thing is still significantly more reliable than the smart boards. So I don't have to sit there and hit the little dots to every single time it starts getting off center. All right. So everybody see how we got to the empirical formula. Last step was it did give us the molar mass of 78 and asked for the molecular formula. So how do we go about that? Good, add up the grams, and again, we can estimate whole numbers, so we can estimate carbon's about 12. So that's about a molar mass of approximately what? 13. So if our molar mass is 78, 13 goes into 78 how many times? 6, which means that what is my molecular formula? C6H6. And there's the molecular formula. Empirical formula, molecular formula. And that is probably the most longest problem from chapter 3. All right. Any questions? Again, this will be posted, plus I did have extra problems. Or you can also just like Google combustion analysis problems, and you'll find lots of tutorials. There is more than one way of doing this, by the way. There is a slightly shorter way of doing this, and I can't remember if on the first tutorial video I might have done it, where instead of going through the steps of going grams to moles to molar ratio back to grams, you can multiply by the percent composition. So either way works. Again, it doesn't matter to me as long as you can get to the right answer. Yes?
Since you won't give us like what it actually is, like the name of it,
Yep.
but you will give us the molar ratio, like the molar mass each time, right?
No, I won't give you the molar masses. It'll just look like this. Combustion of some sample, and I just will take out that. So it'll have this. It won't have the setup. So these molar masses, you have to already know them or know how to find them.
Like total molar mass.
Yeah, it'll give you the total molar mass if it asks you for the molar mass. Yeah, it will tell you that number. Yeah. All right. Let's get to the meat of chapter 3. And by meat, I mean this is the technique that you are going to keep on using all the way through chapter 10. This is a stoichiometry problem. Stoichiometry. This is what I usually mean when I refer to stoichiometry problems, which we will keep on doing through chapter 10. And if you come back in 152, we'll keep on doing it all the way through chapter 20. So stoichiometry problems. Combine the idea of moles and molar ratios, which we just dealt with, moles and molar ratios, with the idea of a balanced chemical reaction. And I narrow this whole process down to 3 steps. But first of all, let's talk about what we mean by molar ratios, and then we'll get into a full problem. So here is a simple reaction. 2 carbon monoxides plus an oxygen make 2 carbon dioxides. So it is already balanced here. So by balancing, that means we have added in these coefficients. So in this case, it's 2 to 1 to 2. These coefficients can be used to make something called a molar ratio. Now, in the last problem, we said, oh, a molar ratio is like 2 hydrogens to every H2O. That is a molar ratio. We can also say that for this reaction, 2 moles of carbon monoxide are needed for every 2 moles of CO2. That is also a molar ratio. So molar ratios can be used to convert between any two species in a chemical reaction. It can go from a reactant to a product like we have here, or it can go from a reactant to another reactant if we had two products between two products. Yes?
What's just the equal sign?
Equivalent to. It just means it's equivalent to. No. So we can take these molar ratios and we can write them as a fraction. So this is exactly what we did way back in chapter 1 with factor label analysis, which was used to convert units. And that's all we are technically still doing is converting units. We're just going from moles of carbon monoxide to moles of carbon dioxide, or vice versa. We're just converting between one species in a reaction to another species in the reaction. So we can use this to convert between any two things in the reaction. Now here's the catch. These are called molar ratios. So what unit must you be in? Moles. Do you think I'm going to give it to you in moles? No. What do you think I'm going to give it to you in? Grams. By now you should be experts at converting between grams and moles though, right?
Yeah.
Yeah, sure. So we can use these molar ratios to convert between any two things in the reaction. We just must first be in moles. Do not skip that step. You must first be in moles. All right. So if we were already in moles, so consider the complete reaction of 3.82 moles of carbon monoxide to form CO2. If I wanted to know how much CO2 is formed, I would just take my moles of carbon monoxide multiplied by my molar ratio. So molar ratios, whatever you started with goes in the bottom. Why would I do that? So they cancel, exactly like units. And whatever I'm asking for how much carbon dioxide goes in the top. So that is what we are left with. Now in this case it was 1 to 1. That wasn't so bad. But let's see if we wanted to know, well, how much O2 is needed to react with that 3.82 moles of CO. So we have our 3.82 moles of CO. Now here's our molar ratio. Again, what we start with goes in the bottom so that it can cancel. What we're being asked for O2 goes in the top. This ratio, molar ratio of O2 to CO is 1 to 2, and we got that from the balanced equation. Go back to the balanced equation. There is 1 oxygen to every 2 COs. So that's 1 oxygen to every 2 COs. Multiply the ratio and we get 1.91 moles of O2. That is the most important step of stoichiometry, assuming you're in moles. Multiply by molar ratio to go from one thing in a reaction to another. All right, so let's try this out. Urea can be synthesized in the laboratory by a combination of ammonia and carbon dioxide according to the following reaction. 2 ammonias plus 1 carbon dioxide makes 1 urea and 1 water. So the first question says, calculate the amount of urea, that's this, urea, that will be produced by the complete reaction of 5.25 moles of ammonia. So I have 5.25 moles of this. So change colors here. .25 moles of ammonia. You know, I'm just going to leave it there for now. NH3. So in my molar ratio, what's going to go on the bottom? Ammonia, right? NH3. What you have drops to the bottom so that it can do what? Cancel. How do I know what number goes in front of it? Balanced equation. So what number goes in front of it? A 2. What goes in the top? Moles of urea. So that's this thing. NH2, I'll just write urea because it's shorter. And what's the coefficient for urea in the balanced equation? 1. So when we multiply these across, NH3s will cancel and we'll just be left still with moles, but now it's moles of urea. So how many moles of urea is that? Good. Yeah, 2.63 moles of urea. How bad is that? Can we do that? All right, now let's add in the extra step of what if we start with grams. I'm just going to jump to the next problem. Nitrous oxide. What do we use nitrous oxide for? It's right there in the problem. What's the common name for nitrous oxide when it's used in dentistry? Laughing gas. Good. This is laughing gas. It's manufactured by heating. That's what this little triangle here means, is that I'm heating ammonium nitrate to decompose ammonium nitrate into nitrous oxide and water. So the first question says, calculate the mass of ammonium nitrate that must be heated in order to produce 10 grams of nitrous oxide. So I want 10 grams of this, and I'm being asked how many grams of that. This is the baseline idea of a stoichiometry problem. You need that molar ratio, but before we can multiply by that molar ratio, we must be in what units? Moles. So our starting amount is 10 grams of nitrous oxide. Blue. 10 grams of nitrous oxide. What is my first step? Good. Convert to moles by dividing by molar mass. So molar mass of N2O. That's 2 nitrogens at 14.01 apiece, plus 1 oxygen at 16. Gives me a molar mass of what? Good. 44.02 grams per mole. That will give me moles of N2. Once I'm at moles of N2, then I can multiply by that molar ratio. You can stop and plug it in your calculator and find it out what it is now, or you can just keep on going. Doesn't really matter. To save space, I'm just going to keep going. So in my molar ratio, what species will go on the bottom? And nitrous oxide, N2O. The N2O. Again, what we start with always goes on the bottom so that it can do what? Cancel. What goes at the top? What I want. I want what? Good. Ammonium nitrate. There's ammonium nitrate. NH4NO3. What is this ratio? 1 to 1. Understood 1 to understood 1. That makes our math easier. So that will leave us with what? And 2O cancels, and 2O, I have ammonium nitrate, but I'm in what of ammonium nitrate? Moles. I want what? Grams. I want mass. So my last step is going to be to do what with this ammonium nitrate? Molar mass. Multiply by the molar mass to get back to moles. So to find the molar mass of ammonium nitrate, we take 1 nitrogen at 14.01 plus 4 hydrogens at 1.008 plus 1 more nitrogen at 14.01 and 3 oxygens at 16 apiece. Adds up to what? Getting 80.05. And that's grams per mole. So now if you haven't already started plugging in the calculator, go ahead, divide by, take your 10 grams divided by the 44.02, times the 1-to-1 ratio, or just times 1, and then times 80.05. Units. Moles will cancel. We're left with grams of ammonium nitrate. I'm going to write it down here because I ran out of space there. Yeah. Get an answer?
18
Eight.
I got 18.18.
Yeah, 18.18. We've got 3 sig figs, so we're going to round that to 18.2. And that's the correct answer. 18.2 grams of ammonium nitrate. So let's take what we just did and summarize it down into the steps that we followed, because these are the steps that we're going to do every time we see a problem like this for the rest of the semester. So is this a problem that you should just, cut bait and say, I didn't understand that, I'll just move on and worry about it later? No, you're going to see a problem just like this in Chapter 4, and just like it in Chapter 5, and all the way through Chapter 10. Again, 152, we'll still be dealing with this kind of stuff. So make sure you have this down. How many total steps did we do here?
A lot.
1, 2, 3. Can we follow 3 steps?
Yep, hopefully.
Yes.
And so our conclusion is that it'll take 18.2 molecular grams of ammonium nitrate to produce 10 grams of nitrous oxide.
Yes.
So the whole point of what we're trying to do is to understand how much nitrous oxide is inside that amount of ammonium nitrate.
The whole idea is if I'm working in a lab trying to make nitrous oxide and I know I need 10 grams of nitrous oxide, how many grams of ammonium nitrate do I put into the reaction chamber? Yep. All right, so let's summarize in words. I'm just going to use this slide, what those 3 steps were. So I call this the 3 simple steps of stoichiometry. Studies have shown people can follow 3 steps pretty reliably, so I'm sure you guys can too. 3 simple steps. So, step number 1, we started with grams. So what was our first thing that we did? Convert to moles. When in doubt, convert to moles. To moles. Step 2, once you're in moles, you can use the what? Mole to mole ratio. Good. And again, that ratio has whatever you started with in the bottom, whatever you're looking for on top. And then that ratio is just your coefficients from the balanced chemical reaction. Step number 3, we were left with whatever we wanted, but we were still in moles. So what was our last step? Convert from those moles to what? Grams. There's our 3 steps. Can we follow them? Maybe. Now, in this particular reaction, we only had 1 reactant. So if I wanted to know how much of that reactant I needed to make 10 grams of my product, it was pretty simple. But what if I have more than 1 reactant? If I have more than 1 reactant, I have to put amounts of both reactants in. And then I have to consider making sure those are balanced, or if they're not balanced, one of them is going to get used up before the other one. So the last thing that we're going to cover today is limiting reactants. Let's move on to limiting reactants. So at this point, I like to give the analogy of cooking. Cooking. How many of you guys have ever cooked a recipe, followed a recipe? Chemical reactions are essentially recipes. Here are your ingredients, here are the products, here are your amounts of each. Those coefficients are your amounts of each. It's just following a recipe. So I'm going to write a very, very simple recipe that anybody could hopefully follow for a cheese sandwich. So I'm going to make a simple, very, very boring cheese sandwiches. So to make a very simple cheese sandwiches, 2 ingredients, slices of bread, slices of cheese. Here's my recipe. 2 slices, bread, plus 1 slice cheese equals 1 sandwich. One very, very boring sandwich. And I say this because this is my 7-year-old's favorite kind of sandwich. Literally, he doesn't even like me to grill it. 2 pieces of white bread, a slice of American cheese. Very boring. I know. All right. So let's say that my 7-year-old brings the whole neighborhood over for lunch without telling me. And everybody wants cheese sandwiches. And I'm going to have to make as many cheese sandwiches as I can possibly make. What's going to determine how many cheese sandwiches I make? How much bread and cheese I have. Let's assume I can't run out to the store. How much bread and cheese I have. So let's say I go into my cabinet and I count up how much bread and cheese I have. Let's say I go into the cabinet and I have, let's change color here. Let's say I have 12 slices of bread. I know. 12 slices of bread. And I've got, let's say, 9 slices of cheese. I'm going to tell my son how many cheese sandwiches is he going to have to feed his friends. 6. Where do we get 6 from? Good. The bread is the limiting factor. Now here's a common misconception. A common misconception students say the limiting reactant is the one you have less of. What do we have less of here? Slices of cheese. But is that what limited us? No, it was the bread. The limiting reactant is not the one you have less of necessarily. Could be. Good. It's the one that you use up faster. So you have to consider what the recipe is, what those ratios are. So in this case, my bread was my limiting reactant. I use the bread to determine how much product I have. So you use the amount of your limiting reactant to determine your product. So I've determined my bread is my limiting reactant because that's what I would run out of first. That 12 slices of bread, 12. Let me write it out as though, I know we can do this in our head, but let's pretend we can't. 12 bread times our molar ratio. Bread goes on the bottom, sandwich goes on top. What is this ratio? What does our molar ratio look like? What over what? 1 to 2. 1 sandwich and 2 slices of bread. Bread cancels. That's where our 6 sandwiches came from. Of course, you did this in your head. I'm writing it out as though you can't, just because the numbers aren't always going to be this pretty, of course. Now, our cheese, if it was it perfectly balanced, or are we going to have leftover cheese? We're going to have some leftover cheese, right? So this is what is called our excess reagent. Our limiting reagent got used up first. Our excess is what we have in excess, what we have left over. How much cheese do we have left over? 3 slices of cheese. Now again, we're going to pretend we don't know how to do that math in our head. To determine that, we're going to take our sandwiches. We know we made 6 sandwiches, and determine how much cheese that's going to use up. So 6 sandwiches times molar ratio again. So sandwiches are going to go on the bottom and cheese on the top to determine how much cheese is it going to take to make these 6 sandwiches. So what does this molar ratio look like? 1 to 1. It takes 1 slice of cheese for 1 sandwich. So it takes 6 sandwiches. Sorry, 6 slices of cheese. Whew. So if it takes 6 slices of cheese, how do I determine how much is left over? Subtract it from what I started with. I started with 9. So 9 minus 6, there's our 3 cheese left over. Oof. Did everybody follow this? If I take the words cheese slices, bread slices, and sandwiches and replace them with chemical names, will you get lost? It's still the same problem, I swear. All right. So the easiest way that I have found to determine limiting reactants and kill 2 birds with 1 stone is kind of what we did in our head here. We didn't really think about it. In our head, we thought, okay, if I have 12 slices of bread, that can make 6 sandwiches. If I have 9 slices of cheese, that can make 9 sandwiches. Which one is less, 9 sandwiches or 6? 6. So the easiest way to go about determining the limiting reactant is to use both reactants to determine amount of product. Whichever one made less product is your limiting reactant, and 2 birds with 1 stone, you've determined your amount of product. So if you follow along with the textbook or YouTube videos, you may see more than one way of doing it. I prefer that way because, again, 2 birds with 1 stone. You've determined the limiting reactant, and you've gone ahead and determined your amount of product. So take your both reactants, do your stoichiometry steps, because it's not already going to be in moles, it's going to be in grams. Do your stoichiometry steps to determine the amount of product each can make. Whichever one made less product is your limiting reactant, and you have determined your amount of product. So let's see this as an example. Alka-Seltzer tablets. Okay, we're still in the kitchen. Still in the kitchen, just now we're dealing, instead of with the bread and the cheese, we're dealing with Alka-Seltzer tablets. Yes? To that one? Yeah. Yeah. So what do we use Alka-Seltzer tablets for? Neutralizing stomach acid, right? Indigestion. You ate too much spicy food, you've got indigestion, you've got heartburn. So there's too much acid in your stomach and it's coming up into your throat and hurting you. So you take an Alka-Seltzer tablet. Now, of course, this is probably a little bit more old-timey. Most people use like Tums now, but same idea. To neutralize that stomach acid. So when you take an Alka-Seltzer tablet and you drop it into water, what does it do? Fizzes, it bubbles, it dissolves, and it bubbles. So here's a chemical reaction that is going on here. Alka-Seltzer tablets are comprised of 2 primary ingredients. Sodium bicarbonate. What's the common name for sodium bicarbonate? Baking soda, right? Again, still not scary stuff. We are still in the kitchen. And citric acid. Citric acid is the acid that comes from what? Citrus fruits, right? So this is like lemon juice, right? Okay, we got baking soda and lemon juice. We're still in the kitchen, still not scary, right? Here's baking soda, here's lemon juice. You can rewrite it as baking soda and lemon juice if you want to. The products of this are carbon dioxide gas, there's our bubbles, water, and then sodium citrate is the other product. This is sodium citrate here. So here's our nice little balanced reaction. By the way, if you're following along with this, this is on page 106 along with a lovely little picture of an Alka-Seltzer tablet bubbling in water. So there's our balanced equation. Let's get to the actual question, though. The actual question says, if an Alka-Seltzer tablet contains 1.7 grams of sodium bicarbonate and 1 gram of citric acid, determine for a single tablet dissolved in water, which one is limiting, what mass of excess reactant is left over when the reaction is complete, and what mass of carbon dioxide forms. Now in this case, in this reaction, we had how many products? 3. So common question I guess asked is, well, if our process is to determine the amount of product made from each reactant, how do I know which product to use? Technically, you could determine the limiting reactant from any one of these products. But looking at what you're going to be asked in the question, which product do you think you want to use? Looking at the questions you're being asked, which one would kill 2 birds with 1 stone if I determine the mass of which product? CO2, because, hey, I'm going to be asked for the mass of CO2. So I can go ahead and use that as the product I care about. I'll get my answer, what's the limiting reactant, and 2 birds with a stone, I'll figure out what my amount of CO2 produced was. So we're going to do those 3 steps of stoichiometry, convert to moles, multiply by molar ratio, convert back to grams. We're just going to do it for both reactants. So we're going to do it for the 1.7 grams of sodium bicarbonate and the 1 gram of citric acid. So let's get some space. So first of all, let's do it for the 1.7 grams of sodium bicarbonate. Sodium bicarbonate. I know we're running out of time today. So step 1, divide by the molar mass to get to moles. In the interest of time, we'll go ahead and tell you the molar mass is 84.01, but you could find that just by adding up the sodiums, hydrogens, carbons, and oxygens. That will give us moles of sodium bicarbonate. Step 2 is molar ratio. So sodium bicarbonate is what I start with, so that's what goes in the bottom. Again, this is just baking soda. What would I put in the top? What am I looking for? The amount of what? CO2, right? So to find what this ratio is, I need to go back to my balanced equation. From sodium bicarbonate to CO2 was a what to what ratio? 1 to 1. You could write it as 3 to 3, or you could write it as 1 to 1. The math will cancel out anyways. We'll just write it as 3 to 3. And now that'll get rid of the sodium bicarbonate and leave us with carbon dioxide. Why did I write carbon trioxide? I don't know. Carbon dioxide. Last step, take that carbon dioxide, I now have moles of it, and doing what? Not its molar ratio, but its molar mass. Good. Molar mass of carbon dioxide is 44.01. And that will give us grams of CO2. We're going to do the exact same thing for the 1 gram of citric acid. 1 gram of citric acid. Let's do the same 3 steps. Gram of citric acid. So the formula for citric acid is H3C6H5O7. So divide by its molar mass. Again, you could get its molar mass by adding up those hydrogens, carbons, oxygens. In interest of time, that's 192.12. Times its molar ratio. So now we're starting with citric acid. Still going to CO2. Go to that balanced equation. So from citric acid to CO2 is a what to what ratio? 3 carbon dioxides to 1 citric acid. And then multiply by the molar mass of carbon dioxide at the end. And that will give you grams of carbon dioxide there. So whichever one of these gave you fewer grams is the limiting reactant, and then answers the question, how many grams of carbon dioxide were formed. So we've run out of time for today, unfortunately. We'll do a few more examples of this on Thursday. Yes?
In this video, we'll be talking about how to do a limiting reactant problem. So a limiting reactant problem can be recognized by a stoichiometry problem where you're given amounts of 2 different reactants and asked for the amount of the product. So for example, an Alka-Seltzer tablet contains 1.7 grams of sodium bicarbonate, that's NaHCO3, sodium bicarbonate, and 1 gram of citric acid, there's citric acid. Determine for a single tablet dissolved in water which ingredient is the limiting reactant being the ingredient that gets used up first, what mass of the excess reactant, meaning whatever one does not get used up first, is left over when the reaction is complete, and what mass of carbon dioxide forms, carbon dioxide being one of the products of this reaction. So an Alka-Seltzer tablet, we're familiar with it, used for heartburn or stomach upset, and when you drop it in a glass of water, you see it bubble as it dissolves. So the 2 primary ingredients are sodium bicarbonate, which is baking soda, and citric acid, which is the acid found in citrus such as lemons. When those 2 come together, this is a base and an acid, they react. An acid-base reaction. Carbon dioxide bubbles are formed, that's when you see the bubbling, and the byproducts are water and sodium citrate. But we're only worried about the one product, carbon dioxide, in this particular question. So how do I determine what the limiting reactant is? Common mistake I see is students assuming whichever one you have less of can be assumed to be the limiting reactant. In this case, we have less citric acid than sodium bicarbonate. But you can't assume that, because if a recipe requires twice as much flour as sugar, then you may run out of flour before sugar, even if you have more flour. Same idea with chemical reactions. We require 3 times as much sodium bicarbonate as we do citric acid. So we may actually run out of sodium bicarbonate first, even though we have more of it. So how do we go about doing this? Well, first of all, in any stoichiometry problem, when we're comparing two things in a chemical reaction, and we see they have a ratio, in this case it is a 3:1:3 ratio, comparing the two reactants and the product that we're interested in. These are molar ratios, so we have to first be in moles before we can make any sort of comparison. We're starting off in grams. So step number 1 of this problem is to convert those grams to moles. So to convert from grams to moles, we do this by dividing by the molar mass. So to get the molar masses of each, we add up the atomic masses of each element. So go ahead and do that for sodium bicarbonate. That is 84.01 grams per mole. For the citric acid, that's 192.12 grams per mole. And then for carbon dioxide, it's 44.01 grams per mole. So let's go ahead and for our two reactants, convert them both to moles. So starting with the sodium bicarbonate, we have 1.7 grams. When we divide by the molar mass, grams will cancel and we'll be left with moles. And then do the same thing with the citric acid. Now at this point in the solution, my method differs a little bit from what you'll see in your textbook if you're following along. I'll be using the method shown in the 2-page spread in figure 3.7. I prefer this method because rather than determining how much of each reactant is needed based on how much of the other reactant, if you go ahead and determine which one is the limiting reactant according to which one makes less product, then you've killed 2 birds with 1 stone, because at the end of that you not only know which one's the limiting reactant, but you've also answered the question of how much product was formed. So I'm going to use that method. So starting with my moles of each reactant, the way this method works is I'm going to go ahead and determine how much product each one made. Now the products, I've got 3 different products here, but the question was specifically asking me for the mass of carbon dioxide. So I'm going to focus on the product carbon dioxide and not worry about the other 2 products. Whichever one of these reactants, sodium bicarbonate or citric acid, makes less carbon dioxide, that one is our limiting reactant. And then we also will know how much carbon dioxide has formed, and we will have answered question C at the same time. So to go ahead and calculate this, we're going to take our moles of each reactant multiplied by the molar ratio to get to moles of carbon dioxide. So for the sodium bicarbonate, so molar ratio is what we're looking for on top. We're looking for carbon dioxide, so carbon dioxide goes on top. And the number in front is a 3. And on the bottom we put what we currently have, drops down to the bottom. We currently have sodium bicarbonate, so that's going to go on the bottom. 3 there. And we have a 3 in front of sodium bicarbonate, so 3 goes on the bottom. That way when we multiply by the molar ratio, the sodium bicarbonate will cancel. And 3 over 3, so the number doesn't change, and we would be producing 0.2024 moles of CO2 if sodium bicarbonate is our limiting reactant. Now let's do the exact same thing for the citric acid. Multiply by the molar ratio to figure out how much carbon dioxide that can produce. So 3 carbon dioxides on top, and we've only got 1, understood 1 citric acid on the bottom. So when we multiply this across, citric acid will cancel, times 3, so we get 0.01562 moles of carbon dioxide. So between the 2 of these, we made less product, less carbon dioxide, when we used the citric acid as the limiting reactant. So that must be our limiting reactant. So citric acid is our limiting reactant. Now, not only do we know what our limiting reactant are, so we've answered that question, but we also know how much carbon dioxide forms, but the question is what mass. So we still have one more step because we don't have mass, we have moles. So just like to go from grams to moles, divide by molar mass. To go from moles back to grams, we do the opposite, so we multiply by molar mass. And the molar mass of carbon dioxide, don't forget, is 44.01. So we're going to take those moles of carbon dioxide and convert them to grams. And now we have our final answer for part C. The mass of carbon dioxide produced. So in the original question, we've answered which ingredient is the limiting reactant. It was the citric acid. We've determined what mass of carbon dioxide forms. So the last part here, part B, asks what mass of the excess reactant is left over when the reaction is complete. So if citric acid is our excess reactant, then the sodium bicarbonate, citric acid is our limiting reactant, then the sodium bicarbonate must be our excess reactant. So we need to determine how much of this was actually used and subtract that from how much we actually started with to determine what mass was left. And I'm just going to leave it in moles for now, just because that's fewer conversions to do. So to determine how much sodium bicarbonate was actually used, we're going to take the moles of carbon dioxide that was formed and work backwards to figure out, well, how much carbon dioxide would be necessary to produce those moles of CO2. And all we're going to do is take our molar ratio from here and flip it. So now instead of CO2 being on top, CO2 is what we're starting with, so it drops to the bottom. Factor label method, back from chapter 1, very beginning. Whatever unit you start with goes diagonal. So if it starts on top, it drops to the bottom. So same deal here as we've been doing since chapter 1. The unit we want goes on top. We want sodium bicarbonate, so sodium bicarbonate goes on top. And the ratio from the balanced equation is 3 to 3. 3, carbon dioxide will cancel, and we'll be left with how many moles of sodium bicarbonate are required. Now, we know how many moles we started with. We started with 0.2024 moles of sodium bicarbonate, and now we're saying that this 0.01562 moles of sodium bicarbonate is how much is necessary, how much was consumed. So to figure out how much is left over, it's a simple subtraction. So 0.02024 moles of sodium bicarbonate we started with, subtract, and this is how much is remaining. But this is in moles, and we want the mass. So again, to go from moles back to grams, we multiply by that molar mass. The molar mass for sodium bicarbonate again was 84.01. So we are left with 0.0388 grams of the sodium bicarbonate remaining. So we've answered all three questions. Which one is the limiting reactant? It was the citric acid. What mass of the excess reactant is left over when the reaction is complete? We just answered that. And what mass of CO2 forms? So we have the mass of CO2 that forms and the mass of our excess reactant that remains. And those are the three types of questions that you will see with limiting reactant problems.